Let's do some worked examples involving volumes of solids of revolution. It's really important to note that the required equations do not appear on the formula sheet, and I think that's partly because having an understanding of where they come from can help you remember them without the need to just rotely memorize it. So it is important, if you haven't done so, to watch the video that goes through the exploration of these formulae prior to this one. So as a reminder, if we are rotating a curve about the x-axis, the formula found for the volume of that solid, we're going from a to b, and you can put the pi inside of this integral or you can put it outside. I tend to like to put it outside, but it is your preference. And we're going to have y squared dx. So y is referring to some function of x, so f of x. So some people prefer to write it as pi, and our integral going from a to b of some function f of x dx. I prefer to think of it, and that should be a squared, shouldn't it? I prefer to think of it as y squared because I imagine the value of y is like our value of the radius of each of those little discs that we're looking at. Now, also, we could be going around the y-axis. And in that case, the volume, again, is going to look pretty similar, but instead we're going from a to b of x squared dy, as in we're going to have the integral going from a to b of some function of y, we're going to square that, dy. So there are two things that it's really important to keep in mind when you're doing questions like this. Firstly, you need to consider, number one. So let's write consider. First off, we're currently focused on volumes of solids of revolution, but you're also going to be learning about surface area. So just like you would have in, year 7, year 8 maths, and you had to be mindful of which one you were doing, you need to remember volume or surface area. So I notice in this first question here, it's talking about the volume. So check that. Next you need to consider is which axis. And this is the one that also can get us into a lot of trouble because, as we've seen, the formulae are quite different. So you've got to know which axis you are rotating around. So this one, we've got a curve, and at first we're going to be rotating it about the x-axis. So in that case, that's the first example we had here. We're going to find a volume, and we've been told we're going between x is 0 to 1. And we need to now write our function f of x. And because we've got that's just y, so instead of writing y, we're going to write x cubed. And we've got to square that, dx. So, as we said, we're going around the x-axis. So I might find it helpful to just put the formula before we do it. So a to b y squared dx. And you'll probably find if you do that, you're less likely to make errors. So we're going to pop that pi back, and our a to b is going to be going from 0 to 1. Our value of y was x cubed, so we're going to have x cubed here, but we need to raise that to the second power, dx. Which that nicely works, because we're going to have x to the power of 7, and divide by that power, and we're going from, again, 0 to 1. So that's going to be, if we sub that in, putting 1 in and multiplying it by pi means we're going to have pi on 7 minus 0, meaning we have a volume of pi on 7, meaning our units need to be cubed. So we can have a little look at this in GeoGebra. I've aligned this so we've got our z, our y, and our x how we normally would, but for questions like this I actually find it useful to align it with the usual y-axis and x-axis. So let's maybe rotate that around. So we can see this curve here has been rotated around that x-axis to form this kind of almost curved cone. It's clearly not a cone because we've got this curved region here, but kind of reminds me of a trumpet or some sort of instrument. And we can see that has been rotated around that x-axis. If we were to rotate that around the y-axis, it'd be a very different shape indeed. So let's continue with our examples. So look at that. As we mentioned, we've now got the y-axis, and we're going from y equals 0 to 1. So in that case, we've considered volume or surface area. We're definitely finding a volume. But now we're going from pi. Our terminals happen to be 0 and 1 again. That is merely coincidence. They could have been anything at all. And with this, I did say let's write the formula before we do it. Good job. A to B. And because we're doing it about that y-axis, we're going to do x squared dy. Now, a little extra work is required here, because remember, this was our equation, y equals x to the power of 3. However, we need an expression with x as the subject. So if we raise everything to the cube root, that means we're going to get x is going to equal y to the power of a third. Okay, so let's put that in. We're going to have y to the power of 1 over 3. We're going to square it dy. So that's going to be neatened up a little. Y to the 2 over 3 dy. And we're just going to apply the simple rules of integration for this. So we're going to have, we're integrating. So 2/3, if we add 1 to that, that's going to be y to the 5 over 3. And if we divide by 5 over 3, that's the same as multiplying by 3 over 5. Going from 0 to 1. So if we substitute 1 in, that's going to be 3 pi over 5. If we distribute out that pi, don't forget about that. And that 0 is just going to be 0. So we're going to get 3 pi over 5 units cubed. So you can see now we're rotating it about that y-axis, not the x-axis, and we're getting that kind of fun bowl shape going around. And that's only in the region from x equals 0 to x equals 1 here. You can see that point. Okay, so very different answers, whether we are doing this about the x-axis or the y-axis, so you need to be especially careful in situations like this. Check whether you're doing volume or surface area, and then check whether you are doing the x or the y-axis that you're rotating around. Let's continue. Okay, so let's do our 2 checks. Volume or surface area. This one is about volume. And which axis? Let's check. It says we're going to find the volume generated with the region enclosed by this curve, the x-axis and the y-axis, and the line x equals -1/2. Okay, and then it says rotate about the x-axis. So you have to be careful there because it's mentioned both the x-axis and the y-axis here, but they're boundaries rather than what we are rotating around. So that's what we're rotating around, that x-axis. So we've done those 2 checks before we've launched into the question. So let's write the formula before we start. Pi going from A to B, and because we're doing the x-axis, we're doing y squared dx. And that's good because this is already written in terms of y. We've got y equals. Okay, so let's pop everything in. The y-axis is when x equals 0, and we've also got x is -1/2. So that means x is going from -1/2 to 0 in this case. And we'll put in our expression for y. We've got 1 over square root of 1 minus x squared, and it's important to square that, dx. Okay, this one's going to be a little more involved than the others we've done before, but nothing that we cannot handle. -1/2 to 0. So, squaring what we've got inside of those brackets just leaves us with 1 minus x squared dx. Now you might see multiple ways of doing this, but when I look at it, I see partial fractions. So we could be going from -1/2 to 0, and we could have, because that can be written as 1 plus x, or you could have written x plus 1, 1 minus x dx. Okay, so we have factorized that denominator, always the first start for partial fractions. So let's go ahead and do partial fractions. So a little bit of a deviation, but very helpful to get us towards our answer. And it's nice to tell the assessor what we're doing. So we've got 1 over 1 plus x, 1 minus x. That's going to be equal to a. We'll have that as 1 plus x. And then plus b. And that'll be 1 minus x. Don't know why I did brackets around that first one. Better. So that means if we multiply everything by that denominator, we're going to have a, and that will be 1 minus x plus b, 1 plus x. Now this one's really nice because we can substitute in 2 nice values, x equals 1 and x equals -1. So we'll let x equal -1 to start off with. In that case, we're going to have the b portion of this is going to go away because we're going to have 1 minus -1, which is 0. So that just gives us 1 equals a and then got 1 minus -1, which will be 2. So a is a half. And if we let x equal 1, well, that's going to get rid of this term here because 1 minus 1. So that means we're going to have 1 equals 2b, so b is also a half. So that means our original situation with these partial fractions, we had a half and a half. So you could put that half here, or you could put the 1 on top and then the 2 out here. But because they're both a half, I think it would be better for us to take that half out as a common factor. So I'll show you what that looks like. Let's continue on with this. So if we take that half out, we'll have pi over 2 there. That's kind of nice. And that means we're just going to have 1 over 1 plus x. And then, oh, we forgot this was going from -1/2 to 0. And then we've got plus 1 over 1 minus x dx. If you wanted, you could do these as 2 separate integrals with the same terminals, if you find that easier to organize your thoughts with. So that gives us pi over 2, and that 1 plus x, that's just going to be a nice log base e of the magnitude of 1 plus x. And because this next one has a negative x here, we're going to have minus log base e of the magnitude of 1 minus x. And that's going from, again, -1/2 to 0. Because we've got that subtraction there, let's maybe jam those together. I'm showing lots of steps of working out, which is not a bad thing. You'll find with more practice, the less you need to do. So 1 plus x is going to go on top, 1 minus x is going to go on the bottom. Regarding my comment of less you need to do, if you find you still need to do lots of working out, that's perfectly fine. I know my working memory is sometimes a bit low, so writing things out I find really useful and helps me remain a little more on top of what I'm doing. Okay, let's do the substitution. So now we're going to have, if we do log base e and we're substituting into those magnitudes 0, that's just going to give us log base e of 1. So that's nice because we know that's 0. And then we're going to be subtracting log e of 1 plus a half is going to be a half. And then 1 minus -1/2 means we're going to have 3 over 2. So we've got pi on 2, and we've got times negative log base e of, we've got 1 over 3 there. But we could rewrite that, oops, not equals, times. Instead of, well, because this is positive, we can just include brackets there now because we don't need the magnitude because we know it's a third. And a third could be written as 3 to the power of -1, and we could put that negative out the front, meaning we've got that negative and now another negative, leaving us with pi on 2 log base e of 3. And nice little thing to know, quite a spread of marks with this question, average of 2.4, 20% of people getting 0. I think those people getting 0 either did the surface area or possibly rotated about the incorrect axis. As we said here, we're rotating about that x-axis, so that means we're going like this. X is that center of rotation, like our axle for a wheel. And this is what that shape would look like. It's rotating around. We've got that little curve here, is this curve here. And we get, almost looks like a bottle cap. It's quite nice. Let's look at the next one. Okay, we've got an exam 2 question, so that is CAS allowed. We've got a region bounded by the lines x equals 0, y equals 3, and the graph of, that one's a little hard to read, it should say y equals x to the 4 over 3. We're told x is greater than 0 and it's rotated about the y-axis, so really important to note. We're also asked about the volume. So the two things that you must always take note of in these questions, which axis, and is it volume or is it a surface area? So for volume, and we're going about the y-axis, it's going to be pi. Now, where is our regions? We're told it's rotated about the y-axis to form a solid of revolution. Maybe it wouldn't hurt to have a quick look at this graph. Okay, so we're interested between the lines x equals 0 and y equals 3. Okay, so that makes sense. Because x equals 0, y equals 0, we can just check that if we weren't sure. So let's do ycal when x equals 0. Yep, y is in fact 0. Didn't want to assume. So we're going from 0 to 3, it looks here. And that's going to be x squared dx. So this is written in terms of y. In terms of x, we're going to cube everything and take it to the power of 1 over 4. So that means y is going to be 3 over 4. So pi from 0 to 3 of y to the 3 over 4 squared dx. Now, we could do more, or we could just pop that into our calculator. Okay, so we get 18 root 3 pi over 5. And another example of when we need to be malleable with how we present our answer, because we know root 3 because we could be written as 3 to the power of a half. So that gives us D as the correct option there. Before we get into the next question, I just wanted to prompt you and ask what would the parametric equations representing this curve shown here, what would they be? So just a little bit of revision, what we tended to do was to write it as a whole thing squared and a whole thing squared when we're talking about our x minus 1. Instead of that being squared and that being over 9, we want to have that 3 also squared. And then we equated the portion that was connected to x to be equivalent to our cos value of t, we'll use as our parameter. And this y over 2 all squared, instead of y squared over 4, we want everything squared inside of those brackets. And that would mean that we could make cos t, and we would rearrange that to be x as a function of t. So x would be 3 cos t plus 1, and y would be 2 sin t. So just a little bit of a reminder, because that will be coming up later on in classes. So the region in the first quadrant enclosed by the graph of blah, the x-axis and the lines x equals 1 and x equals 3 is rotated about the x-axis to form a solid of revolution. So note rotated about the x-axis. It says write down a definite integral in terms of x that gives the volume of this solid of revolution. Okay, to be able to do this, because recall, v would be equal to pi going from a to b of y squared dx. We need to rearrange this so that y squared is the subject. So in that case, we would need to move this over to the other side and multiply everything by 4, giving us that y squared. Don't need to write it as y, because we want a y squared inside of those brackets, so why bother square rooting when we're just going to square it again? So that's going to be 4, and then we're going to have 1 minus x minus 1 squared over 9. Great. So that means we can pop that into this integral, and it doesn't even ask us to evaluate it. It just says write down a definite integral. So we're going from pi, and it said we were going from the x-axis and the lines, it was enclosed by the x-axis, so that's sort of the bottom of it, and the lines x equals 1 and x equals 3. So when we're thinking about where we're going from with the integral with x's, because remember the dx is reminding us that we're looking at the limits of x, it's going from 1 to 3. Y squared we said was equal to 4, and then 1 minus x minus 1 squared over 9 and dx. That's all you need for that. I'm not sure what the mark breakdown of this would have been. Perhaps, I'm only speculating here, it would have been 1 mark for a correct expression for y squared and 1 mark for correctly putting it in the integral. Unsure. I encourage you to pop that into your calculator similar to what we did before and double check the answer that I got. I got 184 pi over 27, and if it's a volume, should be units cubed, but confirm that yourselves. Okay, good luck with your practice and let me know if you have any questions.